So this is the second webinar in the series of artificial intelligence and machine learning. We have two very distinguished speakers today, Dr. Arman Rahmin and Dr. Mathieu Hatt. Dr. Arman Rahmin is from Canada and Dr. Hatt is from France. Next slide, Magdalena, next slide. I'll introduce the speakers. Dr. Rahmin is working in University of British Columbia, Vancouver, Canada. He's Associate Professor of Radiology and Physics. He's Senior Scientist and Provincial Medical Imaging Physicist at British Columbia Cancer Center, Vancouver. He earlier worked at Johns Hopkins University, where he led the high-resolution brain PET imaging physics program. His lab, the Rahmin lab, pursues research in tomographic image generation and analysis. He has published a book, over 100 and also 130 journal articles. He is president for the term 2018-19 of the Physics, Instrumentation and Data Science PIDS Council of the Society of Nuclear Medicine and Molecular Imaging. He has the Laughlin Young Scientist Award by the AAPM in 2016. I think I will also introduce the next speaker who will follow him to reduce the time at that moment. Dr. Mathieu Hatt is working in INSERM, France. He is a computer scientist by profession with PhD in 2008. His main skills and expertise lie in the radiomics, from automated image segmentation to feature extraction, as well as machine and deep learning methods for PET-CT, MRI, CT modalities. He's elected member of EANM Physics Committee of SNMMI Physics. He is working in the Data Science and Instrumentation Council Board of the Directors of IEEE Nuclear Medicine and Imaging Science Council. We will have the presentation by both speakers, and we will have the question answers at the end when both speakers have made presentation. You can use the chat box to provide questions, and we will pick up as much as possible. I can also take this opportunity to mention about the future webinars. The next webinar will be on 20th of this month on CT dosimetry, and then the next one will be in August again on a panel on the machine learning. So this is the webinar on 4th of August on artificial intelligence and machine learning. Next slide. We will have four distinguished speakers in that, the panelists, and they will be talking about the different specialties, engaging in artificial intelligence and machine learning with different specialties. And we have a cardiologist also in that team. So I encourage you to participate in future webinars of IOMP. With that, I will give the floor to Dr. Hatt, Dr. Arman Rahmin, to start his presentation. Dr. Rahmin.
Surely, thank you very much. I hope my screen shows up well. I want to say hello to everyone. I feel very, very privileged to be able to give this talk because I feel that we have scientists and physicists from all over the world joining, and I just feel very connected and at this point. So thank you very much to all for joining. So the topic of today's discussion that I will cover is the field of radiomics or radiomics, and what is its relationship to machine learning and to deep learning. And you can always feel free to send me and Matthew questions to our email addresses. I want to start by my acknowledgements to a number of individuals who really helped me out with helpful discussions and slides, especially Dr. Saeed Ashrafinia with a good number of educational slides that I have used here. So as an outline, we're going to talk about why we like to do quantitative analysis, what is this field of radiomics, what are some of its classes, what is this area of feature engineering, how do you standardize radiomic features, Is there such a thing as multimodality radiomics? What is the relationship to machine learning and deep learning? And finally, is there such a thing as deep radiomics? So just to begin, the visual interpretation is the primary method of assessment in the clinic, of course, as you all know, because it incorporates knowledge of normal uptake, normal variance, and artifacts, etc. However, even though that's the case, it has its own limitations. And when there are, for example, subtle changes, imagine this is a PET scan or a PET CT scan, if in the course of therapy there's subtle changes in the patient's uptake and radiological scan, perhaps a quantitative analysis can allow you to detect things more subtly. And now, there's movement away from pure diagnostic biomarkers towards other kinds of biomarkers, things that look at prognostication, prediction, tracking disease, looking at response to therapy, etc. And each of these could benefit from quantitative analysis. Just to give you an example, I'll show you a number of examples. A good number of them are from PET CT images, but it really is not limited to that field, obviously. The field of radiomics actually started in, for example, in CT, in MRI, and even before that, you had other very high resolution modalities that were looking at this. So here's an example of a tumor that's been imaged. There's many different ways to quantify this tumor. You could measure the maximum uptake in it in the region of interest. You could do some kind of manual segmentation, measure the average uptake. So perhaps, just do different kinds of analysis on this thing. And here's just a very simple example where there's about, I think, 17 patients or so who are being tracked before and after therapy, and the change in the volume of the tumor is being tracked, and the change in the uptake of the tumor is being tracked. And these are three different kinds of responses to therapy that happen with these patients. And what you sort of see is that in order for you to distinguish between these three different kinds of response to therapy, you need both of these metrics. So if we were only quantifying volume of a tumor, that means collapsing this whole plot on the x-axis. If we did that, we could not distinguish between this class and that class. Otherwise, on the contrary, if we were looking at the change in uptake only, we could not really distinguish between this class and that class if we were collapsing on the y-axis. So this just shows that in this very simple example, you needed at least two metrics, not one, to really be able to distinguish between these different responses to therapy. So perhaps we should be looking at more than just one metric. And in fact, if you think about other kind of metrics such as tumor heterogeneity, which could be caused by different things, regional variations in proliferation, cell death, vascular structure, etc., it has implications in disease progression and treatment response. So here's an example where the more heterogeneous the tumor becomes. For example, when a tumor becomes hypoxic, in the case of a PET CT scan, it manifests itself in this kind of a shape where the periphery has higher uptake than the center of the tumor. Well, this is a non-uniform uptake, it's heterogeneous, and we know that hypoxic tumors tend to be more resilient to therapy. So again, there could be value in quantifying heterogeneity of the tumor and not just looking at one or two very simple features. So let's just aim for improved quantification. Take this thing that, the maximum uptake. In fact, believe it or not, in the clinic, on the PET side of things, again, this is just an example from the PET world, but it's not limited to that. Believe it or not, to simplify things in the clinic, people only quantify, typically in the clinic, the maximum uptake of a tumor. So basically, you take this, and you don't need to really segment the tumor. It's so simple to find the maximum uptake of a tumor. You don't even have to just put a box around it. And of course, that's what you measure, and that's what you report in the clinic. But just notice how much information we just discarded to make that simple report in the clinic. But the point is that, there's all this other kinds of information that we should not be probably ignoring. So images are more than pictures, they are data. And this is what this field of radiomics is all about, extracting a lot more information from our images. So this field of radiomics, again, extracts quantitative features from radiological images, which is hypothesized to help us improve diagnosis, prognostication, prediction, and therapy response assessment, and allow us to move towards personalized therapy where each individual is treated and looked at differently in this field. So again, there's a lot of omics going on. We have genomics, proteomics, metabolomics, and in the field of, again, imaging, it's really radiomics that's been happening. So a typical way this is done is you have an image, you segment, for example, a tumor, you extract a lot of features, and then you do some kind of analysis to combine all these features to allow you to improve your assessment of disease. Just to show you one example of a highly cited paper, what you have here is about 400 patients with about 400 features in this work. And what they did was it was totally unsupervised, no knowledge of the outcome. They simply took these patients and sorted them according to their radiomic features. So here's one class, it's unsupervised clustering. So here's one cluster of patients that they ordered and they found, where you sort of see that there's higher uptake for these features and lower uptake for these features. There's a second class of patients they identified where they had lower uptake in this area and higher uptake in this area. And you sort of had a third group of patients that were kind of mixed. So they just found 3 groups of patients based on this unsupervised clustering task. And they showed that this correlates with things like histology, with staging, etc. But in fact, later on, there was a publication a few years later that showed that, you know, you have to be careful, because in this very work, if they had only used the volume of a tumor, they would have done almost the same good job as this complicated analysis of taking all these features and combining them. So it's kind of a wake-up call that when you're doing radiomics, you have to be careful. For example, you've got to look at the volume of a tumor very carefully. You can't just do fancy stuff without paying close attention to simple metrics, because some simple metrics are very good. Volume of a tumor, again, is something that is not routinely reported because you need careful segmentation, and that's a growing field. And again, the field of deep learning is really helping with that these days. But again, Matthew's going to talk about this, I think, later, some of the pitfalls of radiomics that we have to be careful about. But having seen all of that, having been even suspicious of this field, I have come to believe that radiomics definitely has something in it that if we do it in a systematic way. So I'm just going to mention a few feature classes or different kinds of features. You sort of see a list of all kinds of things out there, but I'm just going to show you examples from these red ones. So morphological features, things like, you know, volume of a tumor, for example, or a lesion, you know, or a defect, surface area, how spherical it is, sphericity of a tumor, for example, how compact it is, etc. So there is a hypothesis that, you know, the shape of a tumor is associated with the growth rate, with the aggressiveness of the tumor, etc. So there are studies, again, showing that the shape of uptake makes a difference. So here's an example from our lab where we showed that you know, these are 4 different tumors. They have the exact same maximum uptake, average uptake, but clearly they look very different, right? So it makes you wonder, you know, are these going to have different outcomes? And in fact, there are studies showing that, you know, the less spherical a tumor is, the more aggressive the disease might be. So again, just examples where you have a segmented tumor and you sort of measure a bunch of things. I'm just showing you 2 examples, the maximum 3D diameter of a tumor and the center of the mass shift from the geometric center. So these are just examples, or how solid a tumor is, how rectangular a tumor is, how spherical. This is definitely one that keeps showing up. You know, this kind of a tumor is probably gonna possibly, more likely, statistically going to have a poorer outcome than this kind of a tumor, which is more spherical. So again, studies showing that more spherical versus less spherical can make a difference in the outcome of a patient. Histogramming, you could simply take a tumor, or again, a lesion, a volume of interest, histogram it. Of course, the more heterogeneous the distribution is, the more spread the histogram. So you could measure the variance of the histogram, or its 3rd moment, or its 4th moment, the skewness or the kurtosis. And again, those could give you information. The problem is with histogramming is that it oversimplifies things. Here are 3 different distributions, but they have the exact same histograms, right? 50% black, 50% white. So that's not so great, because you're getting rid of a lot of information when you histogram. You're throwing away the spatial information. So that's why people then look at other kinds of features. I'm going to give you an example from Herelic texture features. It keeps showing up. Herelic texture. You will keep hearing that. Herelic texture features. So here's an example of how this is done. You take a region of interest, you segment it, setting everything else to 0, and then you sort of assign gray levels to this, usually from 1 to 64, sometimes 1 to 28. I'm just oversimplifying here, 1 to 4. So 4 gray levels, but again, usually it's 64, around 64 gray levels. Though there's, again, different ways to do this. You could do fixed bin size, fixed number of bins, etc. I think Matthew might talk about that. So here's an example where you basically have taken these, you just start counting. For example, in this direction, how many pairs of 1 do we have? Well, there's 1, that's it. So 1, besides 1, there's only 1. How many 1s do you have with its neighbor being 2? So, well, there's 6 of them, 1, 2, 3, 4, 5, 6. So we just put 6. So gray level 1 with a neighbor of 2 to its right. How many 4s and 3s do we have, etc. You fill this out, we call this the co-occurrence matrix. And from that, then you extract a lot of features. Things like entropy keep showing up. Entropy is a very good, very interesting, robust feature. You could also engineer your own features, right? So I'm just going to give you one example, especially for this audience, many of which might be very familiar with radiation therapy. So there's this thing in radiation therapy called the generalized equivalent uniform dose. And we sort of took this concept, which basically takes heterogeneous dose distribution and summarizes it into a single number. We said, well, why don't we do that in imaging? So we kind of invented this new feature. We applied it to head and neck cancer. And we showed that if you do it that way, compared to the maximum uptake of a tumor, which doesn't give you as a great prediction, this one might give you a far better prediction. But again, notice I'm not reporting the volume of a tumor, and I should be, and it is in our paper. It shows it kind of a definitely better performance than maximum uptake, but this one is supposedly better. So again, one has to be very systematic. So the metric kind of looks like this. I'm going to go over it very quickly. It's very similar to again, what is used in radiation therapy. It uses the analogy to the LKB model for normal tissue complication probability. And again, this is related to the generalized mean of the uptake. And you can show that this feature that we have is just the generalized mean. This is the definition of a generalized mean. If A is 1, this is the arithmetic mean. If A is infinity, this becomes the maximum uptake. If A becomes very small, close to 0, this becomes a geometric mean, it turns out. I'm saying it very quickly. But essentially, you get the geometric mean of the intensities times this kind of a term that is a volume. So I'm just going to say very quickly, if A is infinity, this thing is the maximum uptake, as I said. If A is 1, you've got the average uptake times the volume of a tumor. If A is less, you're sort of saying the risk is mostly due to the volume of a tumor. If A is more than 1, the risk is mostly due to the intensity of the tumor, and you have things in between. Just giving you examples. Here was an example of a feature engineering. We engineered a feature. So standardization is very important. All the way from the patient to the treatment decision-making, there's many steps that are made in the field of radiomics. First, you obviously acquire the image, you reconstruct the image, you segment the image, you process the image. Then you compute the radiomic features, and finally you put them all together to, let's say, predict outcome in a patient. Well, there's many things that happen here. What resolution do you select? How do you segment? How do you create, how many gray levels do you introduce in your image, etc.? The field of standardization of the metrics is kind of around here. So there's this thing called the Image Biomarker Standardization Initiative, IBSI. You could Google it, you'll find that, you know, that there's a massive group of people involved in this area. Actually, about 25 institutions from 8 countries. The paper was just published. I refer you to this paper in Radiology. And essentially, the idea was, are we all computing the same thing? If we all have the same image, are we going to get the same features? We should, right? If you and I are having the exact same image, are we going to extract the same quantitative values from it? If not, we have a problem. It means our definitions of the metrics or our pipeline, our workflow is not properly standardized. So it started with just having very simple digital phantoms, simply computing metrics like entropy. And you could also have, you know, there were patient data sets where there was a little bit of pre-processing followed by these things. The pre-processing involves, you know, placing the region of interest, interpolation, etc. So when we started doing this, the results were terrible. And this is actually something many people have seen. There's very, very bad reproducibility between different centers. most of the features were very different from each other. This is the same images, but 25 different centers are getting very different values. But over time, when people started talking, when they started to standardizing, using the same definitions of the metrics, going through their implementations of their software, the consistency became much better. In phase 2, with the actual patient images, again, it started kind of looking not great, but then again, after 25 months of efforts, these different centers became much, much more consistent in both of these kind of studies. So there's a number of radiomics packages freely available. I'm just listing here some of them, not all of them. And so there are some links, and which you can see. Radiomics is one of them. LifeX is another popular one. There's, again, other ones that are showing up from different centers. So here's Sarah, our own software package, for example. So these are all freely available for download from these web pages, and again, you can look at those. There's a difference between standardization and harmonization. So for the same image, are we going to get the same features? This is what I just talked to you about. There's also harmonization, which Matthew is going to talk about. But if you got the same patient that is being scanned in different centers or scanners, how consistent will they be? Because different scanners have different reconstructions. So that's even a more difficult problem. It's not just about definitions of features. Now we're talking about making different scanners consistent with each other. So Matthew will talk about that. The time's quickly running out, so I'm going to talk a little bit fast here. You could also do multimodality radiomics. Here's an example of a head and neck cancer patient. Same age, 2 patients, same age. Both are 73 years old, exact same staging, exact same therapy, but the outcomes are totally different. Right? And visually, the clinician might actually read these the same way, but the outcomes are totally different. So here's an example of a paper we published in Fusion Radiomics, where you're combining PET and CT images in this example, but you could be thinking about different features in your own fields. And so maybe you should first fuse the images, then extract the features, or generate the matrices that I mentioned, the co-occurrence matrix, combine those, then extract the features, or just extract the features from PET separately, from CT separately, and just making a big list of features from both PET and CT, and then creating your combination of features. So, applying these 2 different patients, we ended up getting different scores, radiomic scores, and sort of nicely predicting outcomes. So it's something to think about. What is the relationship to machine learning and deep learning? Well, traditional machine learning, what you do is you explicitly define handcrafted features like entropy, maximum uptake, average uptake, different kinds of texture features. And then you feed those into machine learning algorithms. But in deep learning, as you know, and I'm not going to go over deep learning, you kind of give it the raw data, the raw voxel information in the images, and you let the machine figure out and combine these features, so coming up with different representations of the data. So it's a automatic, inherent intrinsic feature extraction. You don't explicitly define the features, you give it the raw data and the machine figures it out. The so-called universal approximation theorem with different kinds of proofs tells you that if your neural networks are tall enough or wide enough, you could approximate any reasonable function. So technically, deep learning can substitute for traditional explicit handcrafted features, but for that you need a lot of data. These things work as the number of layers become more and more and more. You need more and more and more training data because you have so many unknowns. So that's why the field of deep learning really shines when you have a lot of data. But the problem is that in our field, in medical imaging, you don't necessarily have the kind of humongous data sets that industry giants really have, right? So we may be here in medical imaging. Of course, it's important to get more and more data. We may be here. So it's actually not clear at all if deep learning will replace traditional machine learning. So you've got people believing right now, people in very advanced areas of deep learning, that deep learning is not the answer to everything. You could be doing traditional machine learning for certain problems, deep learning for certain other problems. We also did a little bit of evaluation of this, and what we found out is that for a reasonable number of layers with standard architectures that are now in the field, 3D, 2D architecture, state-of-the-art, deep learning, convolutional neural networks, some features like shape is not very easy to capture it by these architectures. So features like shape, especially, like when you're looking at compactness or a volume of a tumor, even with like 5, 7, 9 layers, you could still get a lot of error. So again, the point is, deep learning can perform similarly to traditional machine learning, but that's only if you have a lot of data, and that may not be what we have in our field. So deep radiomics, and this is the final topic I'm going to cover, is a combination between traditional radiomics and deep learning, where instead of giving the raw data to your architecture, to your convolutional neural network, you actually first pre-process it to generate so-called radiomic feature images. So for each voxel, you calculate the local texture, and then you feed that to the thing. Or you take one of the intermediate convolutional layers in your neural network in deep learning, and then you do some kind of radiomics analysis in the intermediate one. Or you look at the final fully collected layer, again, in a convolutional neural network in deep learning, and you do some kind of radiomics texture analysis on that layer. So it's a sort of a combination between traditional radiomics and convolutional neural networks and deep learning. It's not exactly clear if this is going to be the best way to go, but there's some areas of research. It's an area of active research. Final slide, or 2 slides. This is conventional radiology. The clinician, the radiologist, looks at the images, annotates them, archives them. The hope is that the radiology reading room of the future will be a lot more. So you could take the images, the machine will be segmenting for example, different organs, different tumors, extracting a lot of features, perhaps doing some radiomics or AI-based analysis, combining with medical data, genomic data, coming up with a decision support system, and coming back and making a recommendation to the radiologist. Hey, I suggest that you bring this patient back 6 months from now. Hey, I suggest that you put this patient on this kind of a regimen or therapy, etc. So sort of a more active, sort of an automated, computerized environment where the radiomics data or radiomics analyses are used to assist and support the radiologist and the clinician. So without further ado, I stop here and thank you very much.
Thank you, Dr. Rahmin. That's really wonderful. You have provided information on how to extract the quantitative features from images with the potential for personalized medicine, radiomic features, standardization, harmonization, free availability of from radiomic packages, machine learning, deep learning. Thank you very much. It is 5 a.m. for you to start. So it's Thank you. So I already see some questions coming, but we will take them at the end of the seminar, at the end of the webinar. Now I invite Dr. Hatt to start his presentation on potential value and pitfall. Dr. Hatt, please.
Thank you, Madan. Thank you, and good talk, Arman. Thanks for the first part. I'll try to make it a bit complementary with what you described. First of all, I would like to thank all of you to join the webinar. I see that you are almost 450, so that's great, from all over the world, including some time zone that might not be very easy for you. So thanks for joining. So in my talk, I'm going to focus more on the modeling step. I would like to start by stating that any radiomic study, relying on machine learning or not, should actually start with a thorough and rigorous study design before even collecting or acquiring images for your study. You need to start by asking the right questions, such as what's the clinical relevance of the question you want to address? Is it already solved by basic clinical variables, or do you really need to go further to answer the question? Do you have enough data that you will be able to significantly demonstrate the potential benefit or the potential added value of extracting additional information compared to the standard of care, or for just using tumor volume or clinical stage in order to stratify your patients, for instance? Do you have enough data to be able to split your data into training and validation? Are you going to be able to validate your trained and developed models into external data, other cohorts? The potential impact of the findings is going to be extremely dependent on those questions. Again, the curation of the data and how to ensure basic quality checks in your database is also extremely important for the quality and the potential impact of your findings. So currently in the literature, you can find a lot of different papers that have published some guidelines that are now available and that can help you avoid most of the pitfalls and traps in radiomics analysis that can happen in the following of the process. So really, my first advice in that case is to really think about how to design your study and how to make the most out of the data that you have or that you can collect for such a work. I say that because even today, most of the papers that have been published in radiomics are still retrospective studies on monocentric small size cohorts. It's starting to change, but it's still the case mostly. And when you need to collect larger data sets, one of the things that you are going to need is to collect data from different centers, usually, in order to be able to get several hundreds of patients. And as Arman has already said, basically the radiomics features are notoriously known to be sensitive to variations in scanner model or acquisition protocols or even reconstruction settings. So this is something that needs to be taken care of if you need to collect data from different centers and combine them into a single statistical analysis or modeling step. So once you've designed your study and you've collected your data, there are several steps that are going to be almost mandatory, which is preprocessing the data, detecting and segmenting the tumors of interest in your images, for instance, and then extracting features that can be either handcrafted or deep features using pre-trained networks, for instance, as Arman has described before. And finally, you have the modeling step where you are going to try to establish the correlation between the features you have on one hand and your clinical endpoint or decision modeling that you want on the other hand. And in that step, there are a lot of different issues that can be confounding factors and that can limit the potential impact of the models you train. So this is something that we are going to have a look in the next few slides. So just as a reminder, the modeling in radiomics consists in finding the relationship between the clinical endpoint and either handcrafted and or deep network features that you've extracted from the images. Obviously, these features need to be compared or combined with other information that are available, such as clinical variables, just for instance, simple demographic of the patient's data, but also it can be other additional omics data from transcriptomics, genomics, histology, dosimetry information. This is important because the purely radiomics model can be efficient on its own, but it needs to be compared with a purely clinical model or a model combining features from different fields. And then one very important aspect of the modeling is to separate clearly your training data from your validation and testing data. The training data is there, its role is to discover the relationship and to try to build a parameterized model. So here you are going to identify the feature or the features that are the most informative in predicting your endpoints. The validation data, on the other hand, is there to optimize the model's parameters. And finally, the testing data is the data set that is used to actually evaluate the actual performance of the model that you trained, the model that is set with fixed parameters based on the validation data. One of the most simple examples is, for instance, you have PET images and you want to predict the lack of response in your patients. And in the training data, you discover that higher SUV max values is correlated with lack of response or worse response. Then the validation data is going to enable you to to optimize the parameter in stating that a threshold value of 12.6, for instance, of that parameter maximizes the accuracy. And finally, you evaluate that model by applying it directly to the testing data, giving you some performance metrics. If you look at a more complex example, of course, you can try to do the same using a neural network, where you are going to try to build an architecture and build a network then optimize its hyperparameters, and finally, when you have an established network, you apply it as it is on testing data. Ideally, the testing data might comprise several data sets from different centers with varying properties in order to be able to evaluate the generalizability of the models that you trained. Of course, it's often difficult to have data from different centers. That's one limitation. The values I put there for 50, 30, and 20% are just a rule of thumb. There is no absolute rule of the amount of data that you would need to put in each of the data sets, but that's something that's often considered in these studies. So why am I stating that you need absolutely to do this is because the early works in radiomics were really not satisfactory from that point of view. If you look at this review that was published 5 years ago, they highlighted the fact that most of the popular studies that had been published between 2009 and 2014 or 15 were really not up to any standards in terms of statistical analysis. For instance, most of these papers did not include multivariate analysis taking into account the volume. They also never validated the findings in a validation dataset, so they were just reporting correlation in the entire cohort included in the analysis. They also tested a lot of parameters with a very low number of patients without correcting for false discovery in their statistical analysis. So basically, even though all of these studies were showing promising results and led the field to become what it is today, because the number of publications has exploded exponentially. However, none of these studies could be considered reliable in terms of statistical analysis. So we really need to move forward in terms of statistical analysis quality and modeling and robustness of the modeling in those radiomics studies. And this is an example that Arman has talked about before. I want to insist on it because it's a very, very good example of how one very simple mistake or oversight can reduce the value of your study to almost zero, even if you do everything else beautifully and very rigorously. In that study, they used the CT images of lung cancer patients to build and to discover a radiomics signature. So this is the training part on the left here. You can see that they basically enforce feature selection based on their stability with respect to test-retest, but also multiple delineations by different experts. And they enforced the radiomics signature, so that their modeling approach enforced the choice of one feature in each of 4 categories, shape, intensity, and two textural features categories. So basically, instead of blindly selecting features, they enforced the selection of features based on their stability, and they had to have 4 variables from 4 different categories, so they just selected the highest stability in each of the categories. And then this signature was applied to several different cohorts, either from the same or from different centers, and of 2 different pathology, lung cancer and head and neck cancer. And they showed that the predictive ability in terms of survival of that signature was good in both the head and neck and the lung cancer. So they concluded that their radiomics signature was able to capture the heterogeneity of the tumor across 2 cancer types. However, as Arman has said, basically the radiomics signature that was computed was just a surrogate of tumor volume. This was shown last year in that study where they reused exactly the same data set and they recalculated exactly the same 4 features of the radiomics signature, except they did that either on the original image, which is illustrated here in A and B, or by randomizing the voxel locations as illustrated in C and D. So basically you have exactly the same voxel values, except they are randomly spatially placed in the image. And they showed that the radiomics signature calculated on the original or the randomized image was exactly the same, as you can see here in A and B and D and E for lung and head and neck cohorts. And more importantly, it was not better, almost the same as the stratification you obtain using just the volume of the tumor. So really, here you can see that the will to enforce the selection of features only based on their stability and to force the signature to include one parameter from each of the 4 categories led them to calculate a surrogate of the tumor volume, and they did not check that actually. So obviously it reduces the potential impact and the value of the study to almost 0, because there are a lot of different results in that study that are of interest. But in terms of that specific signature and the fact that it's prognostic for both lung and head and neck cancer, it's not really the fact that it captures anything relevant in the image. It's just that it captures volume, and volume is a prognostic factor, a well-known and recognized prognostic factor in both lung and head and neck. So they did not demonstrate anything new. Now, if we want to move forward and do some more robust machine learning to select and combine the radiomic features and also combine them with other variables, obviously in the machine learning field, you have a lot of different techniques available. So in 2015, that paper was one of the first to systematically evaluate what you get, basically by combining one feature selection method with one classification or classifier in order to obtain your result. And this was done on the same data set, the 422 patients from the previous study. And on the matrix on the right that you can see, in white or light blue, you have results that are close to random guess, so they are clinically useless. And the darker you go, the darker the blue, the more accurate you get in terms of survival prediction. And you have some results that are close to 0.7, which becomes to be quite clinically relevant. But you can see that if you choose one single combination of feature selection method and classifier on the same data, you can get something that is completely useless or something that begins to be of interest. So one of the recommendations today is to clearly implement several methods, several machine learning pipelines, and potentially combine them through ensemble or consensus methods to ensure better results and more reliability in the findings. This is exactly the same kind of conclusions that was obtained a bit later in 2018, where they actually included 12 different data sets with different pathologies, different cohorts of patients, and compared 6 different full machine learning pipelines, showing that basically there was not a single machine learning pipeline that was the best across all data sets. So strengthening the observation that you really need to compare and implement several approaches to obtain more reliable findings. Now, about deep learning. Deep learning is, of course, another hot topic in radiomics, as it is in most fields of science. One of the things that we need to remember is that radiomics was established 10 years ago as a machine learning, as a standard machine learning approach. Basically, the input data is the delineated tumor, and you extract handcrafted features that have been previously designed by humans, by engineers, and then you map those features to a specific endpoint. If you want to use deep learning to move that workflow forward or to change that workflow, of course, you can use deep networks to do the classification, to do the mapping, without changing anything else. You can also extract features using pre-trained networks, so in place or in addition to the handcrafted features. And one of the most important aspects is also to automate the whole process. So detection and segmentation of the objects of interest can be more easily automated compared to standard approaches using, for instance, deep networks such as UNet. But you can also consider doing everything together or replacing the entire workflow by one or several deep networks together. And in that way, the input data moves away from the delineated tumors to the entire image, and you just need to train your network to predict the outcome out of the input image. But obviously, if you want to do this, you are going to need larger amounts of data compared to a standard machine learning or standard radiomics approach. This is an example that was published 5 years ago. I think it's one of the first studies that used convolutional neural networks to predict an endpoint using PET images. And even though they had a very small number of patients, they were able to build a strategy where they actually looked at slices of the tumor and used data augmentation to help the training of the network. And they were still able to obtain a better accuracy in identifying patients that did not respond to treatment compared to various different machine learning techniques using standard radiomics features. So still promising, even if you have a small amount of data, deep learning approach could lead to better automation and more accurate results, especially if it's combined with a standard radiomics approach instead of just replacing it. Now, the last thing I want to talk is the harmonization. As we discussed before, when you want to have a larger number of patients, you are going to need to collect data from different centers usually, especially if you want more than several hundreds of patients. One issue is that it's been shown clearly that most of the engineered features are extremely sensitive to even small variations in voxel size, reconstruction settings, or even scanner model and kernels in the reconstruction. So if you want to harmonize this, one solution could be to process the images so they are more similar to each other before features extraction. And there also deep learning can be extremely useful, especially with all the developments in image synthesis. So this is an example that was published last year where the images with different reconstruction kernels in CT were generated to be more similar to each other. And you can see that comparing the column on the left and on the right, you can see that the stability of the features increases drastically when they are extracted from images synthesized with similar kernels compared to the original images. This is just to illustrate here visually, you have the original image with one kernel and the other kernel, and the converted image so that it looks more like the kernels in the middle. So to conclude, the radiomics analysis in terms of modeling and machine learning are full of methodological pitfalls, but there are a lot of solutions available today. Most of them actually do rely on machine learning techniques, such as for harmonizing images or for selecting and combining features together. There are guidelines that I recommend to follow as much as possible to improve and to prepare study design as much as possible before starting anything. And in that context, as Arman has described before, the standardization of good practices and the nomenclature and the definition are really key aspects to improve reproducibility and to compare results amongst groups and between papers. Clearly, if you want to collect data from different centers, be extremely careful about the variation and the variability in image properties that require harmonization. And overall, it's clear that the deep learning techniques are going to be more and more important to either improve or replace the usual radiomics workflow, but also to bring improved automation and better results in the future. So with that, I'd like to conclude. Thank you for your attention. And of course, I'm available for the questions.
Thank you. So nice. And the main key message is everything is not gold and so many issues involved and how machine learning. Maybe you will like to switch on your video, Mathieu, if you want. Okay, the time is very limited, so we have to see how to handle the questions. Let's start with the one for Dr. Rahmin. The question is relating to the raw data rather than re-extracting data from the image.
Yeah, so I think that's an interesting question. I mean, radiomics itself per se has really been only applied to images. But the idea of looking at the true raw data, looking at the truly raw data, not the raw image, but the raw data before it's reconstructed, that's clearly showing up now in the field of AI, where people are thinking about the idea of can we learn patterns from the images, from the raw data for whatever outcome. So there's some research going on, and I don't mean for improving the reconstruction. I mean literally going from the raw data and its distributions, the patterns in it, to detecting disease or to predicting disease. So that's really showing up, not in the field of radiomics per se, but in the field of AI, where what people are trying to do is applying deep learning models primarily to the raw data to see whether they can improve. Because I mean, the question is a good one, because often when we reconstruct an image, we may lose some information, some spatial information, etc. However, when we look at raw data, the problem is that we don't have the intuition as much as we have in the images. So I think there's debate about whether there's value. And that, I think, brings me to another question, which is a black box question. You know, do we sink into the black box trench when we look at deep features or deep radiomic features? I think there's really different approaches to this. It's almost two schools of thought about this black box issue. There is definitely push against the idea that, you know, it's black box is a problem actually. So some people say, you know, any sophisticated technology has a black box component to it, and it can be indistinguishable from magic if it's working really well. And some of them say, you know, you look at the human mind, we don't actually understand how the human mind works, but it works. But there's a totally different approach to this, and that is to say, look, we need to gain understanding and depth, and when we don't understand exactly what's going on, we may make mistakes too. So I think there's definitely increasing push towards interpretability of these models. What do they really mean? So in the field of radiomics, when you have explicit texture features, there is increasing efforts to correlate those with pathologically meaningful phenomena. In the field of AI or deep learning, for example, too, there is increasing push to trying to understand what these models mean. Are they interpretable? So I think there's definitely these two schools of thought are clashing, but I think it's a healthy clash. It's a healthy tension. One of them says, don't ignore and discard the great successes that these fields may have. The other one says, we have a long way to go. We need to gain more understanding.
Thank you. I think I'll have a question for Dr. Hatt. Which is better, deep learning only and conventional machine learning plus radiomic features?
Clearly, it depends on the amount of data that you have, and also on the control that you can have on how you build your models. It's easier to select and to base your feature selection in standard radiomics based on external knowledge, such as how reliable how repeatable are the features, and also the meaning that you can put behind the features that you define. The difficulty, on the other hand, is to choose, select, combine the different standard machine learning techniques to build your models. The advantage of deep learning is that you get higher automation, and that you get better features that are the most optimized and suitable to the task at hand. However, given the limited amount of data that you have, usually, even if you have hundreds of patients, it's still a limited number of data points from the point of view of deep neural networks. So then you replace the challenges by others. You need to find appropriate data augmentation techniques. You need to rely on transfer learning using pre-trained networks that you are just going to fine-tune to your actual data. So in both deep learning, purely deep learning, or purely standard radiomics approaches, you have challenges and you have things that you need to overcome. They are just different. And I think that deep learning can help radiomics, but it will never replace entirely radiomics or standard radiomics, as long as you don't have thousands and thousands of patients to train your model. In both cases, you are going to face challenges that you need to overcome. And I think that at the moment, they are more complementary to each other than they are opposite methodologies.
Confounding factors, somebody is asking. Can you talk about that?
Well, the most obvious one is to forget about checking the correlation of the features that you extract. whether they are deep features extracted or standard radiomic features, with the usual variables that you have on hand. Okay, if your deep or radiomic model predicts survival exactly the same way as age or gender or even tumor volume, it's useless. Okay, you need to demonstrate that what you are extracting from your images is complementary or provide additional value with respect to all the variables that you already have on hand without even looking at the images. Okay?
Thank you. A question for either of you, how radiomics will impact patient care in low and middle income countries?
Yeah, that's a pretty good question. I think I mean, clearly the broader area of AI is definitely going to have impact because, you know, it's going to make certain things, certain pipelines, sort of workflows more accommodating in different environments. And I think it might improve certain tasks. Radiomics per se itself, it's kind of it's very hard to predict the future. If I may share a slide here for just 1 second. I just want to show you something literally. This is not necessarily answering the question about the developing countries, but it is good to have in mind. I mean, the future of radiomics is not very clear, but I just want to show you a linkage between radiomics and radiation therapy. This is just a hypothesis that in the future, this might be the way of the future, possibly. Again, be very careful. I'm not suggesting to do this right now, but once radiomics is done well, and there's a lot of obstacles left, potentially in the future, you could sort of have routine pipelines where, for example, you have an image here, it is delineated by the physician, but the radiomics might identify, you know, high risk or low risk components of an area of interest. And then based on that, the amount of the boost or the dose delivered in the context of radiation therapy might be altered. So I think this is a way of the future, and I think it will impact, have a worldwide impact. But again, we are quite a long way from that. And maybe not a long way, but we have to sort of really work hard to make sure that we're systematically doing things correctly. So that was just an excuse to really show you this slide from this kind of interesting review by a number of colleagues to just make us all think about how radiomics is going to impact healthcare in general. Especially in the context of radiation therapy, where a lot of the audience today is in.
Thank you. Thank you so much. I think we are just at the time to finish. So let me take this opportunity to thank both of the speakers and all the participants and Magdalena who helped in technical matters. We are going to have series of webinars. The next one is on 20th of July on understanding the limitations, and then on 4th of August on further webinar with 4 panelists. Thank you very much for your attendance, and thank you both speakers, in particular Dr. Rahmin, very early in the morning, 5 a.m. starting, so you must have got up for 4:30 or even sooner. And thanks to all those who are from different time zones, very, very extreme time zones, and thanks for your participation. Have a good night, good day as applicable.
Indeed.
All the best.
Thank you.
Bye.
Bye. Thank you very much to everyone.
Bye.
Thank you for the invite, and thanks for all people attending.
Yep.
Bye.
Thank you. Bye.